In every corner of your home, hidden inside a simple plastic dome, lies a marvel of modern engineering that defies the traditional laws of heat and light. For over a century, the world relied on the incandescent bulb, essentially a burning wire inside a vacuum. It was inefficient, fragile, and hot. Today, we use the light-emitting diode, or LED, but this isn't just a better light bulb. It is a solid-state quantum machine. It contains no moving parts, no gases, and no filaments. Instead, it relies on the movement of electrons through a synthetic crystal to generate illumination. This process, known as electroluminescence, allows a tiny chip, smaller than a grain of salt, to outshine a bulb 10 times its size. Imagine the precision required to manipulate matter at the atomic scale just to light up your kitchen. This is the story of how sand, rare minerals, and raw physics are transformed into the most efficient light source in human history. We are diving deep into the microscopic world of semiconductors to see how we've harnessed the power of the quantum realm to banish the darkness one photon at a time. The journey begins not with glass, but with sapphire. Because the internal components must survive extreme precision and heat, engineers start with a thin, circular slice of synthetic sapphire called a wafer. This wafer acts as the soil where the light-growing crystal will live. Inside a high-tech furnace known as an MOCVD reactor, short for metal organic chemical vapor deposition, the air is sucked out to create a vacuum. Then, gases containing gallium and nitrogen are pumped in. At temperatures exceeding 1,000 degrees Celsius, these gases break down and the atoms rain down onto the sapphire wafer, arranging themselves into perfect rows, atom by atom. This layer is called gallium nitride. It is the heart of the LED. To make it functional, engineers must dope the crystal. This means purposely introducing impurities like magnesium or silicon to change the electrical properties of the material. One layer will have too many electrons, while the next will have too few. This creates a tension, a microscopic battery ready to be triggered. If the layers are off by even a few nanometers, roughly the width of a single strand of DNA, the entire batch of thousands of chips will fail. This is manufacturing at the limit of physics. To understand why an LED glows, we have to look at the quantum well. Inside that gallium nitride sandwich, there is a meeting point called the p-n junction. On one side, we have an excess of electrons. On the other, we have holes, which are essentially empty spaces where an electron should be. When you flip the wall switch, electricity forces those electrons to jump across the gap into the holes. This jump is a massive drop in energy. In physics, energy cannot be destroyed. It must go somewhere. In an LED, that excess energy is spat out as a single packet of light called a photon. The color of the light depends entirely on how far the electron falls. In gallium nitride, that fall produces a deep, piercing blue light. This was the impossible step that took scientists decades to master. Without blue LEDs, we couldn't have white light or the screens on our smartphones. Every time an electron finds a home, a tiny spark of quantum energy is released. In a single second, this happens trillions of times, resulting in a steady, flicker-free glow that consumes 80% less energy than a traditional bulb. Once the wafer is grown, it is sliced into thousands of individual dies, or chips, using high-powered UV lasers. Each chip is smaller than a pinhead. Now, we must connect this microscopic crystal to the human world of wires and plugs. This is the packaging phase. A high-speed robotic pick-and-place machine grabs a chip and glues it into a silver-plated copper frame using a thermally conductive epoxy. But a simple glue-down isn't enough. To carry the current, a machine called a wire bonder performs a feat of high-speed precision. It takes a thread of pure gold, 5 times thinner than a human hair, and welds it to the top of the chip. Using ultrasonic vibrations, the wire is fused to the semiconductor in a fraction of a millisecond. Gold is used because it doesn't corrode and is a superior conductor. This tiny golden bridge is the lifeline for the LED, providing the electron flow that powers the quantum well. If this connection is weak, the bulb will flicker or die prematurely. The machines work at a blur, bonding up to 10 chips per second with sub-micron accuracy. It is a dance of robots and precious metals, working to build a light that can last for 20 years. There is a problem. The LED we've built only glows blue. If you put that in your ceiling, your house would look like a futuristic laboratory. To get the warm, soft white light we crave, engineers use a clever bit of alchemy. They cover the blue chip with a layer of yellow phosphor. This phosphor is a chemical compound that absorbs some of the high-energy blue light and re-emits it at lower energies, mostly in the yellow and red spectrum. When the remaining blue light mixes with the new yellow light, our eyes perceive it as pure, brilliant white. By subtly changing the chemical recipe of this yellow glop, manufacturers can control the color temperature of the bulb, from the sterile daylight of an office to the cozy, warm white of a living room. This coating process must be perfectly uniform. If the phosphor is too thick, the light looks muddy and dim. If it is too thin, the blue leaks out, making the light feel harsh. It is a delicate balance of chemistry and optics, turning a cold, scientific blue into a warm, inviting glow. LED is a sensitive electronic component. It hates the electricity that comes out of your wall. Your home runs on 120 volts of alternating current, AC, which switches directions 60 times a second. If you plugged an LED directly into that, it would explode instantly. To bridge this gap, every LED bulb contains a driver, essentially a miniature computer and power plants tucked into the base. This circuit board uses a bridge rectifier to turn AC into DC, and a transformer to step the voltage down from 120 volts to a meager 12 volts. High-quality capacitors are added to smooth out the ripples in the electricity, preventing the flicker that causes headaches and eye strain. This driver is the most common point of failure. While the LED chip can live for 50,000 hours, the heat generated by these electronics can bake the components. That's why engineers pack the driver with heat-resistant resins and protective coatings. It is a silent guardian, conditioning the raw, dirty power from the grid into a smooth, constant stream of electrons for the semiconductor to consume. LEDs are famous for being cool to the touch, but that's a bit of a trick. While blue light itself is cool, the conversion process still creates heat concentrated in a tiny area. If that heat stays on the chip, it will cook the semiconductor, causing it to dim and eventually fail. This is why the body of the bulb is an engineering masterclass in thermodynamics. The LED chips are mounted on a metal core printed circuit board, MCPCB. This board has a layer of aluminum or copper that acts as a highway for heat, pulling it away from the chip and toward the base. In many bulbs, the plastic housing is actually a thermally conductive composite, or it masks a hidden aluminum heat sink. This sink uses the surface area of the bulb to radiate heat into the surrounding air. Unlike incandescent bulbs that radiate heat forward as infrared energy, LEDs push their heat backward. Engineers must design the airflow and material density to ensure the junction temperature never exceeds 85 degrees Celsius. It is a constant battle between the brilliance of the light and the destructive nature of heat. How do you guarantee a product will last 22 years? You don't have time to wait 22 years to find out. Instead, engineers use accelerated life testing. In the final stages of manufacturing, random batches are pulled from the line and placed into burn-in racks. Here, they are subjected to the torture test. They are turned on and off 50,000 times in a row to stress the driver circuitry. They are placed in high humidity chambers and ovens set to 60 degrees Celsius to simulate the hottest attics and harshest climates. Specialists use integrating spheres, giant hollow white balls, to measure the exact lumen output and color accuracy of the light. If the color drifts by even a few kelvins, the batch is rejected. Every bulb must also pass a high-potency test, where a sudden surge of 3,000 volts is sent through the electronics to ensure it won't catch fire during a lightning strike. Only after surviving this gauntlet of fire and electricity are the bulbs cleared for packaging. It is a grueling process to ensure that when you flip your switch, the light is perfect every single time. The final assembly is a high-speed marriage of components. The driver is snapped into the flame-retardant plastic housing. The aluminum plate with the LED chips is pressed on top, often with a dab of thermal grease to ensure a perfect heat connection. Then comes the optics. Because an LED chip is a directional light source, it only shines forward, it would create a harsh spot of light if left uncovered. To fix this, an A-line dome, or diffuser, is fitted over the top. This dome is made of a specialized polycarbonate loaded with microscopic glass beads or frost. These beads scatter the light in every direction, mimicking the omnidirectional glow of an old-fashioned bulb. The base is then threaded with the classic Edison screw, made of nickel-plated brass. Automated soldering points secure the input wires to the tip and the ring of the base. Finally, a laser engraves the technical specifications onto the side, the wattage, the lumens, and the safety certifications. The transformation is complete. What started as raw sapphire and sand is now a consumer product ready to light the world. The LED bulb is more than just a convenience. It is a global revolution in energy. By replacing the inefficient heat of the past with the quantum precision of the present, we have reduced global energy consumption for lighting by nearly 75%. But the engineering doesn't stop here. We are now entering the era of smart lighting, where the drivers inside these bulbs contain Wi-Fi chips and sensors, allowing us to change the color and intensity from our phones. We are seeing horticultural LEDs that use specific recipes of light to grow food in vertical farms, and human-centric lighting that mimics the sun to help us sleep better. From the depths of a sapphire wafer to the ceiling of your bedroom, the LED is a testament to what happens when we stop trying to burn things to make light and instead start manipulating the very building blocks of the universe. It is a quiet, glowing reminder that even the simplest objects in our lives are powered by the most complex science imaginable. The next time you flip that switch, remember the trillions of electrons falling through a crystal just so you can see. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this tech archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.